Hey everyone, welcome to the lecture for section 9.5 on alternating series. So in this section, we're going to see a lot of connected material. So I think there's going to be about 8 examples broken up into maybe 3 or 4 videos. So to start, we'll look at Theorem 914, and it just says that if you have an alternating series of this form, where a sub n is positive, or of the second form, then it's going to converge if both things are true. The first thing is that a sub n has to go to 0 as n goes to infinity, and you have to have that the sequence is decreasing, right? So that's listed here as a sub n plus 1 is less than the term that came right before it. And again, it doesn't have to be true for all n, it just has to be true for all n past a certain point. So let's look at example number 1. So this is an alternating series. Here we have that a sub n is equal to 1 over n, and that is 0 for all n greater than or equal to 1. So we have that it's in the form of the alternating series, right? So we need a sub n to be positive, which it is, and we're in this second form down here, -1 to the n plus 1. And so now what we need to do is we need to determine whether or not a sub n goes to 0 and whether or not it is a decreasing sequence. So the form is correct. It is an alternating series. And then next we need to check that the limit as n goes to infinity of 1 over n is 0, which it is. That's a really straightforward limit. So another check. And then we also need to see that a sub n plus 1, which would be the term 1 over n plus 1, is less than 1 over n, which is the nth term, a sub n. And so this is definitely true as well, because as the denominator increases, the term will decrease in value. So check, check, check. Once we do all 3 of those things, we can conclude that our series converges. So notice this is looking like a harmonic series, but we have the flip-flop of positive and negative signs. So this is called the alternating harmonic series. So now let's look at example number 2. So we're going to use the alternating series test again here, and our series is n over -2 to the n minus 1. And so the first thing we have to check is form, right? We have to make sure that this is in fact an alternating series. So the way that we can do that is if we write the series like this. So here it is in its original form. And I really need it to be of the form where I have -1 to the n or the n plus 1 times something that's positive. So I'm going to factor out a -1 in the following way. First, working inside the parentheses of the denominator. So I have -1 times 2 to the n plus 1. And then by the way that exponents work over products, I'm going to get n over -1 to the n plus 1 times 2 to the n plus 1. And I don't need to keep -1 to the n plus 1 on the bottom in the denominator. I can write it like this. So now I have it in the correct form, and I can see that a sub n is equal to n over 2 to the n plus 1, which is positive. So form, check. The next thing I want to check is the limit. So I want to take the limit as n goes to infinity of n over 2 to the n plus 1. And so clearly the exponential will overtake the polynomial on top, but just to be sure, you can apply L'Hopital's rule here. And you would get the limit as n goes to infinity of 1 over, let's see, so 2 to the n times 2. So this is going to be 2 times ln of 2 times 2 to the n, which is the same thing as 1 over ln of 2 times 2 to the n plus 1. And so as n goes to infinity, we can see that this limit will be 0. So that's taken care of. And then the other thing that remains is that we need to make sure that for sufficiently large indices n, that a sub n plus 1, which equals n plus 1 over 2 to the n plus 2, is less than or equal to, let me just double check on the inequality. Yeah, is less than or equal to n over 2 to the n plus 1, which is the nth term, a sub n. And so this is the part that might need a little bit of work. In order to show this, I'm just going to cross multiply. Since everything's positive, I don't need to worry about changing the sign. So I'm going to get n plus 1 times 2 to the n plus 1. And I want to see if that's less than or equal to n times 2 to the n plus 2. And I can actually cancel out 2 to the n plus 1. So this is going to be n plus 1 less than or equal to n times 2. So again, just dividing each side by 2 to the n plus 1. And then here I'll get that n plus 1 is less than or equal to 2n. Or I could write 1 is less than or equal to n. And this is true for all n greater than or equal to 1. So then that checks out as well. And then we conclude that this series also converges. So in this next example, we'll see how it can fail. And we're still good. Our form here is still good, right? We're still in the alternating series form where a sub n is equal to n plus 1 over n, which is positive. So we're good there, but where we're going to fail is if we look at the limit as n goes to infinity of a sub n, which is n plus 1 over n, this equals 1. So this is, we kind of failed on that second condition. The alternating series test does not apply in this case. Because we weren't able to check off all the boxes we needed to make our conclusion, it's basically useless. It's not telling us that it diverges. It's just saying we don't know. The alternating series test will not tell us that whether or not this converges. So the alternating series test does not produce any conclusions. However, you could use the nth term test for divergence. And that'll show that this series diverges. But again, we didn't learn about the divergence of the series from alternating series test. We got that only from the nth term test for divergence, and that's in section 9.2.